Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you for coming, and for people who are watching online. We are very happy to have with us Abik Roy Chowdhury. Abik is actually an associate professor. Sorry? Yeah. Abik is an associate professor at the National University of Singapore, and he earned his PhD from Stony Brook. He's actually been there for almost 10 years now. He has very diverse interests, ranging from embedded systems to software testing and analysis, symbolic execution, etc. So he's actually going to talk about some of his work today.
Okay, thank you. Okay. So should I begin?
Yeah.
Okay. So this talk will be on the role of symbolic execution in software testing, debugging, and repair. And essentially, even though I will talk about some specific techniques, I'll try to go into the role that symbolic execution is playing in each of these techniques. Okay. So of course, first of all, I must mention that the growth of symbolic execution that we have seen in the software engineering community in use in different software processes, this is driven a lot by the SMT solver technology maturity. Okay. So without the growth in SMT solver technology, many of these techniques would not be possible. And the purpose of this talk is really to see whether this can be used, symbolic execution can be used in newer ways in software engineering. So of course, there is a process-centric view, that is whether symbolic execution can be used beyond testing and verification, where it has conventionally been used. So for example, I'll try to talk about how it has been used in debugging and repair, where conventionally symbolic techniques were not used. But also I think there is a conceptual view, and that is symbolic execution is quite a bit has been used for guiding search in a large search space, and whether one can go beyond and try to use symbolic techniques for inferring intended behavior. And really, what is the secret recipe that makes symbolic execution drive both of these roles, that is guiding the search in a huge search space as well as inferring the intended behavior of programs? Because of course, as you might imagine, if you can infer the intended behavior of a program, then debugging activities like debugging become much more tractable. So really speaking, the perspective that we are taking for symbolic execution in this talk is that conventionally it has been used quite a bit. When I say conventionally, it is conventionally now, but some time back it was not so conventional in test generation, model checking, and so on, where it is exploiting the similarities in the search space. And also at the same time, it can be used, symbolic execution can be used as some sort of a psychiatrist trying to uncover what went wrong. And this is really the role that is being played by symbolic execution when we use them in debugging, summarization, semantics extraction, program repair, and so on. Okay. So when I talk about debugging in this talk, I should very clearly clarify the difference between the bug hunting and debugging. Of course, in many of the papers which use model checking for finding bugs, this is also mentioned as debugging, but that is really bug hunting, where you have a certain property in mind and a program, and you produce a counterexample, and the counterexample essentially says that okay, under these input conditions, this property is violated. Whereas what we are mentioning here as debugging is that there is a certain input, there is a certain output, and we are actually trying to find out what went wrong in this particular test case. So this is really the debugging problem that we are looking at. So here a certain property is not given to us. What is the property that was violated? This is what we are trying to find. But on the other hand, we have a failing trace. Okay, so this is the debugging problem that we are looking at. Yeah.
And you explicitly want the property or the part of the code that's...
Yeah, we want the part of the code which is the likely suspect for the violation of the expected output.
And then, so then a property is much more general than the piece of the code.
That's right, that's right. So we really won't be inferring the properties in debugging. That's right, yeah. So I think these are the things that I believe I can skip. So there's the, of course, you have symbolic execution. You just replace the input with a certain theta, and then you have the concrete output as well as the symbolic output. So the symbolic outputs are given in terms of theta. And of course, the path in symbolic execution, we have quite a bit of usage of path conditions. Where in this case, given the input equal to 5 corresponding to each line number that is executed, you can keep track of an assignment store and a certain path condition. And the path condition really captures the set of all inputs which go through this path. Okay? So at any point of time, you can keep track of the branches that you are going through. The branch conditions, and for any branch condition that you are conjoining, you can look up the symbolic store, and this is how you can compute the path condition automatically. Okay. So in our usage of symbolic execution, we will be having a fair amount of usage of path conditions. And the usage of these path conditions has been fairly extensively popularized in this directed automated random testing method, where you continue the search for failing inputs, and in particular inputs that don't go through the same path. So for example, the aim here is really to get path coverage. So for each path, you capture the path condition and you negate a little bit of it. So for example, if you start with this bold path, this is the path condition, and you negate a little bit of it, and you get another path condition, and you try to get a solution for this. You negate a little bit of it more, you get another path condition, you get a solution for this, and so on. So the aim is really to make sure that you don't have inputs which go through the same path again and again and again. So this is a fairly well known at this stage, a fairly well known usage of symbolic execution in testing. So there is, when you use dynamic symbolic execution for testing in this way, there is some sort of an implicit assumption. And the implicit assumption is that the inputs that execute a certain path are similar. Okay? So if you test one of them, there is no need to test the others. Okay? So essentially that we are using similarity to skip over parts of a large search space, and the dynamic symbolic execution is essentially a tool which helps us achieve this goal. Okay? So the first thing that I'll mention today, and that is a usage of symbolic execution again in test generation, is whether one can look at coarser-grained notions of similarity which are useful for test generation. So this is a slide which shows the different roles played by symbolic execution in testing, debugging, and repair. In testing, really the goal is always that we don't need to test for similar inputs, and there is the possibility of looking for similarity beyond paths, that is probably combining paths into one single partition of paths. In debugging, of course, given a failing input, we are trying to find out similar inputs which pass. Okay? So we will see that one can do logical comparisons to detect the deviations between these failing inputs as well as the similar inputs that pass. And finally, in repair, there is the question of finding similar inputs which show the same error, and therefore you can rescue them all, and this forms the search space of all possible repairs. And here also symbolic execution, we will see, is used to capture the intended behavior of the program. Okay? So this is how I'll try to set the stage for the usage of symbolic execution in testing, debugging, as well as repair, and at all points of time try to go back and see what role symbolic execution is playing in each of these techniques. So let me start with an example technique from testing. So this program actually has 8 paths, not surprisingly, with the 3 branches there are 8 paths, but we can see that they can be partitioned into just these 3 partitions based on the symbolic outputs. So if you take the input-output relationship, that is captured the output as a symbolic expression in terms of the inputs, then these are the conditions under which you have different symbolic outputs, that this is the condition under which the output is 2. Here the output is x, okay? The x and y and z are the inputs, and here the output is y. So this is another notion of similarity which one could use, which probably goes beyond the directed automated random testing. And it would be nice if we could compute these path partitions automatically. Of course, I am just defining these path partitions here. I haven't said how to compute them. So if we could compute these path partitions automatically, this is the kind of a summary that we will generate for the program. That under these conditions the output is 2, under these conditions the output is x, under these conditions the output is y, and so on. And it turns out that it is possible to compute these path partitions actually automatically if you do a bit of dependency analysis over and above symbolic execution. So instead of computing the path conditions on the paths, we compute the path conditions over these so-called relevant slices, which is essentially an extension of the backward dynamic slicing. So the dynamic slicing is a closure of control and data dependencies, the dynamic control and data dependencies. The data dependencies are just the use definition chains, and the control dependencies point out to the closest enclosing branch. So over and above these control and data dependencies, which capture the effect of all the statements which affect the output by getting executed, we also have these so-called potential dependencies, which capture the effect of statements which affect the output by not getting executed. So for example, here I have this example here. This is actually a potential dependence because of this branch, because this branch got evaluated in a certain direction, this statement did not get executed, and this affected the output. Okay? So if you also capture the effect of these statements which did not get executed and thereby affected the output, and combine it with dynamic slicing, and you compute the path conditions over these extensions of dynamic slices, you can really try to uncover the transformation function underlying the program. Okay? So this is clearly much beyond the directed automated random testing, because you compute these partitions. So I will not go into the details of these properties, but these properties are important for the search to be complete. So here we compute these relevant slice conditions, that is the path conditions over these relevant slices over the different paths. And the property that we have is that given a path, if an input satisfies the relevant slice condition, if an input t prime satisfies the relevant slice condition of t, then its relevant slice condition is the same. So really these are the inputs which compute the same symbolic output. So now the search will proceed exactly as in directed automated random testing. You start with a random input, you go through its path, you compute the relevant slice over that path, you compute the relevant slice condition over that relevant slice, and this captures a whole group of inputs who have the same symbolic output. And now you have to modify this relevant slice condition a little bit so that you can move into another group of inputs which have a different symbolic output.
So if you took the straight line program, translated it to bounded model shaping, then the relevant slice condition is like an all set with that formula.
So
all set, I mean, it's an all set with respect to projection criteria, which is the output.
Yeah, so there are
enumerate model.
The relevant slice condition will capture all the statements which actually affect the output. So I will essentially,
Symbolic model.
yeah, so this is all because of the inherent parallelism in the program. So there might be number of statements and their conditions which appear in the path condition but do not affect this particular output.
But
Yeah.
the question is really, suppose you translate your program directly to logic, what does the relevant slice condition mean? And I was
It is-
suggesting the answer, oh, it's all set.
Uh,
It's a DNF enumeration with respect to a projection.
The relevant slice condition is a relatively dynamic concept. It's not a static concept that given the conversion of the program into the logic, I will be able to get a notion for the relevant slice condition. So given a path, if I start with a random input, given a path for that input, it is a projection of that path and the logical representation of that projection.
So is it a formula in terms of the input symbols?
Absolutely.
Okay.
Absolutely. So just like the path condition, it is a formula in terms of the input symbols. So you think of the path condition, it's like many of the conditions in the path condition are filtered away, and this is because of the inherent parallelism in the program. They were probably not relevant for the computation of the output.
But you don't know based on a single path, you don't know which conditions are important and which are not, right?
Based on the single path, I can know by doing this dependency calculation over the path.
So that actually looks at the entire procedure, the dependency analysis.
The dependency analysis will look at the trace. Yes. Yeah.
But it seems like much of the time it's not really even the output that matters for symbolic execution kinds of problems. It's whether, oh, I don't know, you hit some sort of a, buffer overrun, or which might actually not even affect the output. Or if you say consume a lot of memory, or if something else, kind of some sort of a secondary condition that follows that's not captured by these predicates at all.
That is true. That is true. So here I am doing the path exploration and the path partitioning based on the output. So it could be that the definition of what you want to test is not captured in the output. You are just trying to look for crashes and so on. That will not be captured by this path exploration. That's correct.
But is there a way to do that? So suppose I have a memory consistency check that goes and traverses my allocated data structures and does some
Yes.
bookkeeping.
Yes.
Is there a way to do something around that?
Yeah, of course. You can actually make it observable. You can define that as the output. And then once you do the path partitioning based on that input-output relationship, it will capture the different partitionings. Absolutely. So if you are looking for specifically a buffer overrun, you can define certain output conditions which capture the buffer overrun, and you can do the path exploration and the path partitioning based on those output conditions. Absolutely. But we did not do that specifically in this work. Here, when I say as output, these are really the output variables of the program. Yeah.
So if I think of it, this relevant slice condition is an abstraction of the path condition.
Absolutely.
Okay.
Absolutely. So it throws away all the things in the path condition which are really not relevant for the production of this output. Yeah. So there is a technical details here which I am skipping. So this we actually proved that the path exploration based on these relevant slice condition will really explore all the symbolic outputs. That means there is a completeness in the search which was relatively difficult to prove. And the reason for this is actually the property that is shown below, that in a path condition, if you have a certain path condition, if you negate part of it, okay, then you can be sure, if you negate say one of these constraints, then you can be sure that the path condition of the input that contains this negated formula this contains this formula as the prefix. Okay? But in the relevant slice condition, because since it's a slice, actually some of these branches might disappear when you compute the relevant slice condition. And as a result, we have to do some reordering. But this is a more of a technical details for the sake of proving the completeness of the search. Once you do this, the validation is really as expected, that these are all the programs, and then the relevant slice condition was of course much smaller than the path condition, and then the paths explode through the relevant slice condition. These are also much less, because of course many paths are online getting grouped into this relevant slice condition. So this is one usage that we looked at. Yes, sorry, there's a question here.
Does this assume that, I mean, I don't know what these programs are, number one. Number two is that, does this assume you can actually run them in this model, if you will, end to end?
Sorry, say that again.
Does this assume that you can actually run them to the end in this model and capture everything that you need to capture?
That's right.
So what are these programs?
So
How big are they?
what are these programs? These are all from I think the SIR, what we call the software infrastructure repository. Yeah.
So how many lines of code?
So I think these are not particularly big programs, say about less than equal to, I think most of them are less than equal to 1,000 lines of code. Yeah.
So you can basically explore them fully.
Yeah. Yeah. But I guess the issue is that even if the program has, say, 100 lines of code, if you just migrate from one group of paths to another group of paths, you have to make sure that the search does not diverge, and you will actually compute all the symbolic outputs, compute partitions for each of the possible symbolic outputs. That is what we showed in the completeness of the search. Sorry, there's a question here.
How would you relate this to summaries? So if you create a summary for a block, basic block, would you uncover some of the related functionality of
Absolutely. So this is absolutely a summarization procedure. Even though we used it for test generation, this is absolutely a summarization procedure, and it could benefit if the basic block summaries were available.
Yeah, but the techniques are different, as far as I understood.
Yeah. So here you could think of that I am trying to uncover the transformation function underlying the program somehow. And as you might imagine, there could be unboundedly many symbolic outputs. Unboundedly many symbolic outputs also, not just concrete outputs, but symbolic outputs, as a result of which there could be unboundedly many path partitions. So definitely I cannot show that the search in this way will terminate. But if there are finitely many and boundedly many symbolic outputs, then I will have exactly that many path partitions, yeah, and that many test cases.
So are you inlining all the procedures, or are you doing them compositionally here?
Oh, no. I'm not inlining anything. It's interprocedural.
So these are the number of paths per procedure? I mean, do you use the summaries?
This is the total number of paths that were explored.
So when you do interprocedural, if
Yeah.
there is a call, do you use the summary of that call, or do you inline that call?
No, that would be the way of improving the search. In this case, these are really the traces. You see, I am working with traces here. I start with a random input, I look at its trace, I do the slicing over that, then I do symbolic execution over that slice. Actually, the slicing and the symbolic execution are going hand in hand. That produces a formula. I do some operations on the formula, negate it, produce another formula, and then that moves on to the next path partition.
Right, but these are
So-
really interprocedural traces, right? And
Yes,
when you
yes.
compute the summary, it's a summary of the entire program.
That's right.
Not for a given procedure.
That's right. So
So
if
it's
I
not
actually,
compositional in that sense, right?
you could say it that way, but if I actually did put in the summaries of some of the lower level procedures, then it would be faster, but then of course it would be less accurate, because then I am just treating the whole summary of the underlying procedure.
And what is the output for you here? I mean, the programs have their implicit output.
Yeah, the programs have their output, and I am just using that output.
The heap is not considered part of the output.
This was one of the questions. Yeah, we could make the heap as one of the output. We also did that. Yeah, that's a good question. Yeah. Yeah. Okay. Okay. So maybe I'll move on. Okay. Right. So I'll mention to you one way we have used symbolic execution for debugging, where conventionally symbolic execution was not used. And this is in this domain of regression debugging, and here you will see that the role of symbolic execution is very different. In regression debugging, the problem is very simple. You have a test input, it is given to an old stable program and a new buggy program, and earlier it used to pass and it now fails, and you want to know why. So here there is, this statement is a little bit informal, but then the assumption here is that when you try to go from the old stable program to the new buggy program, you probably try to add some new functionality. The intended purpose of the old functionality is as before. Okay, so therefore this should not have failed, but now it fails, and you want to know why. So this would be a very first thing one could try, because in debugging literature conventionally there has been a lot of usage of trace comparison. That is, the test input is fed into the old stable program and the new buggy program, and you produce paths. And whether you could directly compare the paths, of course you cannot directly compare the paths, because these are really two different programs, and they might have completely different algorithms and data structures and so on. So it wouldn't be feasible to directly compare the paths. But the question is whether you can generate some sort of a new input. You could generate some sort of a new input using this evolution information, and then you can compare the behavior of this new input with the buggy input to find out what went wrong. Okay, so this is what we are trying to do in the debugging problem, and this is a schematic to give the intuition of the debugging method. That here you have the buggy input. Say these are the partitions. Here this is just a schematic. These are the partitions. Assume that all inputs in a bin are similar. Now what is similar? This is up to us to define what is similar. And in this case, say the red input is the buggy input. Because of this error that has been introduced, it has somehow shifted from one partition to another. What we are looking for is something like this blue input, which was similar in behavior to the red input, but now is different in behavior, but this blue input has not changed its behavior at all. Okay? It is the red input which has changed the behavior because of the error that was introduced, and we are trying to look for a blue input like this one, which is now different in behavior. So this is really the intuition. Sorry, you seem to have a question.
It seems like the unstated assumption here is that your properties of interest are not data dependent, they are sort of symbolic formula dependent. Which is to say, it's possible to have exactly the same formula that will, in practice, yield very different outcomes, especially when interacting with systems you're not capturing, like databases, right? In a traditional example, you have a SQL injection, which is the result of concatenating a bunch of strings. The formula is always the same. It's concatenating string A, string B, and so forth. Yet, for some devious inputs, it produces a very different outcome. And you see what I mean?
Mm-hmm. Yeah.
So there's this issue of data dependency versus computation dependency that you're not talking about here.
Yeah, that's correct. So I did not state that exactly what these partitions mean. Somehow there is an unstated assumption here that the error is visible in the control flow. If these partitions actually capture the control flow in some way, we did some other work where this assumption, we can go past this assumption, but I'm not presenting that technique today. But in this particular technique, that is the case. Yes. Okay, so in this first work that we did on debugging using symbolic techniques, there's this test input which is fed into the old stable program and the new buggy program, and we do a concrete and symbolic execution, compute the path conditions of the test input in both the programs, and then essentially we will compute solutions for this formula f and not f prime, because these are exactly like the blue inputs, which are similar to the buggy input in the old program and different from the buggy input in the new program. Okay, and this gives us an alternative input And actually there is really no need for us to do the trace comparison. We can just look at satisfiable subformula from this f and not f prime, and that would give us all of these symbolic execution is actually happening at the level of the assembly code. This will give us the bug report at the assembly level, and then we reverse translate it back to the source level. Okay. And the reason there is no need to do any of the trace comparison for the solutions of this f and not f prime is that, of course, there can be many solutions of these ones, and we don't want to explore all of them. But note that the f prime is a path condition, which is a conjunction like this one. So, of course, when you look at look at the negation of this not f prime, you can consider all possible deviations of it. So it could deviate off in the first branch, the second branch, the third branch, and so on. So if the path condition has m constraints, you only really need to look at most m equivalence classes. And for each of them, each of those deviations, you really know which line would go into the bug report. So it is that particular branch that will go into the bug report. So if the path condition has m constraints, you really have to look at m of those formulas, check which of them are satisfiable. Any one that is satisfiable, you just put the corresponding branch in the bug report. So this is how the technique works.
So it seems that any branch that could avoid the error will be reported, right? Any branch that you can just take a different path and avoid the error will be reported. So you're not taking into account the similarity of the two paths here, right? You can just diverge at the first control location, first branch, and then just go off somewhere.
Yeah.
Right.
So
your new path might be somewhere, might have just the first branch as common, and the rest is completely different.
yeah, that's actually a good point. We had some other strategies for prioritizing among these ones that are satisfiable, whether they are also successful, the inputs that we generate by solving those deviations, whether they are also successful, because those could be also failing inputs, and those ones we don't want to consider in the bug report. Yeah. So now, if we have this picture, we can also employ this coarser-grained similarity that I mentioned to you, that is look at these path partitions instead of paths. So we can just use these relevant slice conditions instead of the path conditions, and the whole technique would just be used for free. And in which case, as you might imagine, the results become much better. In fact, of course, I'm showing you these are much bigger programs than the ones that we showed for the test generation. I think the Nano XML, JLX, JTopus, I don't have the exact sizes, but these are much bigger programs. And you can see that the size, both in terms of the size of the path conditions and relevant slice conditions, in this case we have the time for doing the debugging, which is substantially cut down. And also the lines of code, because each line of code is really coming from each of these deviations that we record. So each line of code is a branch condition that is given by each of these deviations. So many of the deviations just get filtered out because of the slicing. Okay, and of course, many of the other results that we had in the original work on Darwin, which was, by the way, built on BitBlaze, the BitBlaze tool, so which we are thankful because they made the tool available to us much earlier. They were also replicated. And since this technique is completely based on semantic analysis, one can use it on different implementations of the same protocol also, for example, different web servers and so on. We also used a different variation of this method on finding out errors in embedded Linux by validating it against Linux, the busy box. These are exactly the errors that are reported in the Klee paper. They did the test generation, and we did the root causing of all of these errors. Yes. Yes.
So here, did you intersect the relevant path condition with the diff to only focus on the?
No. This is just the relevant slice condition as produced.
The root cause for
Yeah.
the regression.
Yeah.
the branches that you report, do you also consider whether they are present in the diff?
No. Actually, we don't do that, and that is really the one of the observations behind building these techniques, because the error might not be in the diff. The error might very well be in the original program itself, but it might not have been manifested, and it is now getting manifested. So we are never doing the intersection with the diff. Right. So. And finally, I show you one usage of the symbolic execution in program repair, and this is something we have actually worked on recently. So here, when I say program repair, the correctness specification is given by a test suite. So when we repair the program, the purpose is to make sure that it passes all the test cases in this test suite. And the repair strategy, I'll go through the repair strategy in a minute. And the usage of symbolic execution here is to group together all of these executions through which a failing execution could be rescued. So in some sense, this is a newer notion of similarity. This result was just in ICSI this year. So let me show you the problem with an example. This is a very simple example. This is just a simple procedure without any loops, and suppose the error is in line number 4, where the bias equal to down sep. We would like to have this corrected to this bias equal to up sep plus 100, and suppose these are all the test cases and 2 of the test cases in fact fail. So the purpose is to generate a new expression for bias excuse me, so that these test cases actually pass. So the first step of this method is the fault localization. Here we are using a statistical fault localization method, which actually takes in the program and the test cases and tries to find a line which somehow appears more in the failing test cases and less in the passing test cases. There are many metrics for that. We are using one particular metric that is used by this tarantula tool. And so what we need to know for understanding the method is that suppose this method has pointed you one particular line, in this case line number 4, how you can correct that expression, the bias equal to down sep, to bias equal to up sep plus 100 automatically. Okay, so this is what the repair method is doing. And of course, you can try doing this for one line at a time. If it doesn't work, you can try to go to the next line that is given by the statistical fault localization method.
Is there a specification for each of these examples, or is there some null pointer violation?
There is no specification. So my only goal is to make sure that the repaired program passes all the test cases. The specification is given.
Have an oracle in that?
That's right. So for each test, we have the input and the expected output. Yeah. So the first step is to go to this line, find the suspect, and the second step is to find out through symbolic execution what it should have been. Say, if your aim is to correct the bias equal to down sep, so you just replace bias with x and go on doing symbolic execution from there. So you are doing concrete execution up to that particular line which you want to correct, and then subsequently you go on and do symbolic execution from there. Okay, so you can see here, so I replace the right hand side with x, and the path condition is true at this point of time, and then you can go on forward, and in this case you develop one particular path condition, x greater than 110, in the other one x less than equal to 110, and so on. And it turns out that this one leads to a passing execution and this one leads to a failing execution. Okay. So just to make this a bit more concrete, so this is really, at this point of time, I put this as a function of all the variables which are live. Okay, this is really a function of all the variables that are live, and I'm trying to synthesize a function of this form, which takes in all these variables that are live. And I know the values of each of these variables because I am trying to rescue this particular test case. So if these are the values that were actually fed by this particular test case, I want to synthesize a function which satisfies this formula. This was obtained from the path condition that we got. Okay. Excuse me. So, so corresponding to each test case, we will accumulate each of these constraints, and I am trying to find out a particular function f which satisfies all these constraints, and we can fix the set of operators that appear in f. This will be done by a program synthesis. So there are a number of methods in which you can generate the fixes. Either you can search over the space of expressions. In this case, we will actually use a program synthesis. And finally, the generated fix is of this form. So I can go through this in a little bit more detail. So the first step is the producing the ranked bug report, where we are using just an off-the-shelf statistical fault localization tool. For the symbolic execution, we are trying to group all the paths which can avoid the error. So if you have this line which you want to fix, you just replace it with a certain variable x, and then you do symbolic execution with x as the only unknown. So this would be actually fairly scalable because the symbolic execution is only this particular variable. Okay, and the x is nothing but the function over all the live variables. So this is really the function that you are trying to synthesize. So at some point of time, you can just add this constraint that x equal to the function of all function over these concrete values, and this would actually implicitly generate constraints over this function. And this is the function that you want to synthesize. So this is what we call the repair constraint. And you get a repair constraint of this form. Of course, we don't feed this off to the SMT solver just like that. We will select some primitive components that can be used in this function, and this is done through some sort of a layered search. So initially, we can see whether there can just be, these can just be constants, constant function, if not maybe arithmetic operators, if not logical operators, if then else, and so on. Sorry, there's a question.
So there's a set of benchmarks collected for grammar-based synthesis.
Okay.
So the way you describe that, your application fits directly into those benchmarks by Pennsylvania, UPenn.
So I am actually using, we are actually using an extension of the program synthesis method based on input-output pairs which have been developed here. Yeah. Yes.
But Allure, there's a website where they're collecting this benchmark.
I'm not aware of that one. So
okay, I found the name.
Okay. So, but the technique that we are using, this synthesis method, this is an extension of the IO pair-based synthesis method which has been developed. Yes. Yeah. So instead of directly feeding this formula off to the SMT solver, we are looking for a program that uses a given set of primitive components, and the components, we are searching for these components through some sort of a layered search. And of course, the questions are where to place each component and what are the parameters for each component. So the way this is done is essentially we define the location variables for each component, and then we get constraints on the location variables. So the simple example that I have here, this is the only component is just a plus, and these are the location variables. This is the location variable of the input to the program. This is the location variable to the output to the program, the location variable for the output of the plus, of the first input of the plus, the second input of the plus, and so on. So just this assignment of the location variables gives me the program, and that gives me the expression to synthesize. Okay, so it will generate a constraint system on these location variables, which will be solved to get an assignment to these location variables, and that gives me the program to generate, and that also gives me the expression that is to be synthesized. So actually these are the subjects that we used. Again, the first set of subjects are from the SIR, the software infrastructure repository that we use in software engineering community, and also some others from the GNU core utils. These are the utilities like mkdir, mkfifo, copy, and so on. And here in the repair, actually this is really the first work that uses any kind of semantic analysis for repair. This I can say with confidence. In the past there was a lot of work. There you have probably heard of the GenProg tool, which does repair by using genetic programming. So we also try to look for these benchmarks or subject programs against the GenProg tool. And both of these were repaired by the GP as well as the SEMFIX tool for the GNU core utils. Even though, surprisingly, even though our technique uses symbolic execution, it was faster because the symbolic execution is used in a fairly scalable fashion with very few variables. Does it matter? Yeah, you will see whether it matters or not. Okay, so these are the, I think I will convince you that it does matter with this slide. So you can see here the correctness criteria is given by the number of test cases. Okay, so of course if I add more and more test cases, my correctness criteria becomes more stringent, right? So whatever was a valid repair earlier may not be a valid repair anymore. So now you can see the graph for the repairs produced by this GenProg tool and the repairs that we are producing, which is the blue line. So the repairs that we are producing are much more stable, and the reason is it is actually based on analysis of the paths. So later on, if you add test cases which go through the paths that were already tried out earlier, then of course the repair that was valid earlier will continue to be valid. Okay. So this is not surprising that ours is much more stable, whereas here you can see the one that is by GenProg, this is producing by genetic programming. So effectively it is trying to get the repaired expression from somewhere else in the program by moving it to the buggy site. And the repairs that are produced are not valid as you add more and more test cases. And these test cases were not cherry picked by us. These are actually, each of these programs come with a predefined set of test suite, okay, which were produced by some sort of a coverage criteria. So first we take 10 of those randomly, then add 10 more randomly, 10 more randomly, and so on, just to do the experiment in a proper way. Yeah? Yeah?
But are you prone to overfitting more so than GenProg, the other way around?
Overfitting. I'm not sure.
In other words, the size of the model, I mean, you can basically generate a program that would do perfectly on 50 or so, 45 or so test cases.
Okay.
But that program will be really hideous and special casing for every one of those test cases.
Yeah, but of course, means you can always repair the program like if you knew the test cases, then if this, then this. If of course we are not doing that, yeah, right? There would be no way. The technique doesn't know what the test cases are going to be fed. It cannot possibly know. Yeah.
The confusion I had was when you're trying to synthesize the F function.
Yeah.
You're not doing it on a single failing test, right? You accumulate all the failing tests.
Absolutely.
And then you feed it to the synthesizer.
Absolutely, yeah. So the repair constraint actually generates constraints on the F function for each of the tests. And of course, doing it for each of these tests, that may be a bit cumbersome, so there are some optimizations for doing that.
And
yeah.
You're saying that if you increase the set of tests, this F becomes unsatisfied. You cannot, if you throw in hundreds of tests, then the synthesizer might not be able to give you.
Yeah, what I said, yeah, because all of this were done in a time budget. Yeah, so it does not mean that the repair that was produced, it says that the repair that was produced is not a valid repair. Does not mean that if more time was given to the GenProg tool, it may not be able to produce. That we don't know. Of course, at some point of time, you have to put a time budget. Yeah. Right, and you, in fact, this is another slide through which you can see whether it matters. These are all the different classes of errors, say constant error in constant, arithmetic errors, comparison errors, logic errors, code missing errors, and so on. And this is the comparison between the GenProg tool and this semantic analysis based fixing. You can see that the GenProg tool doesn't seem to be doing so well in some of the categories, where in some other categories it is sort of okay. Okay. Yeah.
Genetic programming was used for analog circuits and repair synthesis. It's a very different domain.
Mm-hmm.
So, could you use any of these techniques from the semantic fix for analog circuits?
I have not explored that.
I think COSA was
Okay.
doing that.
Yeah, I really have not explored that. Yeah, yeah. But certainly it would be feasible, I think. But I have not explored that at all. That's an interesting connection. I have not even thought about that. Yeah.
But that was like a killer app by John COSA. In his 50 proc supercomputer in his garage or outhouse. And that's what they were doing. But GenProg is tailored for software.
Yeah, yeah. It is tailored for software repair, for program repair.
But it tries to borrow repair chunks from the program itself, which is not necessarily the best of ideas.
Yeah. Essentially, maybe I am oversimplifying a little bit, but essentially it is trying to copy expressions from somewhere else in the program.
So if it's never found there, then
Yeah. It does these mutation and the crossover operations. Of course, in the mutation you can change a little bit, but it becomes very difficult to synthesize a real fix with those kind of operations. Shuvendu, you have it.
More from MaxSat-based repair by Rupak. Did you look into that?
Yeah, we did look into that. So there's the MaxSat-based debugging.
Right, and then the section of repair as well.
Yeah, but I guess they did not look into repair that much. Yeah, it's more the debugging that is essentially in fact, in a later manifestation of this work, we are trying to use certain variations of MaxSat for repair. In this case, as you saw, we are essentially just fixing one line, but one could probably try to fix together several lines at the same time, lines that are correlated, and whether MaxSat or such techniques can be used. That's a possibility. Okay, and just to very quickly go through, so even though there is just one line fix that we are generating, it's also possible to, because the lines can be fairly complicated, you can synthesize missing code, or you can have if then else's within the fix that you are generating, and thereby have this operations, this other capability less than altered value, if so then 3 reports valid, and so on. So this is a fairly complicated fix that is being generated. So just stepping back, in terms of the repair, of course there are, I don't think of course it will be completely automated. So there is the issue of building programming environments and putting the human in the loop, and I think in the repair the program synthesis is likely to play a useful role. Is debugging required? This is a little bit questionable to me. So as the first step of this repair, we put the statistical fault localization, which already goes to the line, and then I try to repair that line. Maybe that is not needed. So one could think of repair methods which does the testing and repair hand in hand and avoids the statistical fault localization altogether. That means you, through some symbolic execution, you try to generate test cases, and as the test case actually fails, you try to repair these test cases that you found. So this is probably an answer to your question that you mentioned just now. One could find the location to fix via this symbolic reasoning as well as MaxSat. So I think there is a possibility. We have been trying this out, but this is not very scalable. So there are difficulties with this. And of course, there is the issue of suggestions, generating suggestions instead of repairs. We have tried to look into the usage of this for generating repairs of access control errors and so on. which is a different story. So just coming back to the theme of this talk, which is the perspective played by symbolic execution. So even though in test generation, model checking, verification, the symbolic execution is being used essentially to guide the search, that is, you try through symbolic execution, you play the role of many concrete executions, whereas in debugging, repair, summarization, program semantics extraction, somehow the symbolic execution is playing the role of uncovering what went wrong as well as discovering the intended behavior. All of these are somehow exploiting, all of these techniques are built in such a way that they are exploiting similarities in large parts of the search space. In the case of debugging, for example, among the deviations, in the case of repair, trying to find out all the test cases which need to be rescued together, and so on. So I think there is a fair amount of space to cover in this for these two different roles of symbolic execution. One is the discovering of the intended program behavior, and the other is the guiding of the search. And of course, just very briefly, let me mention one possible take from today's discussion. The symbolic execution tries to infer the intended behavior. We also did just one other work where we directly try to capture the intended behavior through this change contract specifications. So there has been fair amount of work on program contracts where you try to give input-output specifications of programs. So here we try to look into change contracts where you describe the intended behavior of the changes. So for example, the contract at the bottom is saying that when these input conditions are when these conditions are satisfied and there are no input conditions, whenever the output, the previous output satisfies this condition, the new output should satisfy this condition. So these are really, you can give output specifications between the outputs of the two program versions rather than input-output specifications, which is more flexible, I guess. And let me just conclude by giving you these references as well as thanking all my co-authors, and I will be happy to take any more questions.
So we have visual summaries, which is similar to the change
Right,
contract.
right, yeah. We have discussed that before.
One other thing that I
Yeah.
wanted to say was, I mean, I guess you're giving too much credit to symbolic execution. If you're looking at program verification, there's a much nicer encoding to logic, and that sort of reduces the problem of path explosion. So you might be able to do a lot of these things if you were to do this VC generation based encoding into logic. Right?
That is true. Yeah, actually a lot of the techniques that we did were dynamic symbolic execution.
Right.
Yeah, that is a symbolic execution over specific paths. Yeah. At least one of the initial observations to me was that specifically for reasoning about regressions, where you have a past version of the program, or for reasoning about cases like embedded software where you have a reference implementation of the program, you can use symbolic execution over this reference implementation or the past version to get some hint of the intended behavior. And for software engineering activities like debugging, if you have a hint of the intended behavior, it is a huge plus. And this is really the problem, that we don't have formal specifications in the program. If I had lots of formal specifications for each of my methods, then things like debugging, there really wouldn't be much to worry about. So symbolic execution definitely was helpful in that regard, in the absence of these formal specifications, somehow to get a hint of the formal specification. So in that is one of the credits that I am giving to the symbolic execution. Apart from the known usages of symbolic execution like guiding search and so on, but those probably could be done by other methods as well, as you already mentioned. But the finding of the intended behavior, probably I couldn't be doing that through verification methods, because the verification methods require a certain property to verify.
You can specify the program as a property. The previous version of a program can be a property. So
That could be. Yeah.
All I'm saying is that you can encode any of these things into logic directly.
Sure. Sure, that could be this one.
Then all the questions will thank a week once again.
Okay, thank you.